but I'm going to turn it over to Ben Beale, who is going to talk to us about optimizing soil fertility for forages. Ben is also with University of Maryland Extension. He is the agriculture extension educator down in St. Mary's County. So I'll let you take it away. Thanks, Ben.
Alrighty, thanks Amanda, and hopefully you can see the screen and hear me okay.
Yep, we can see and hear you.
Great, okay, so I'm going to spend the next half an hour, 40 minutes or so going over some of the basics of nutrient management for forages. I do want to, at the onset, recognize Amanda, who first gave this talk at the Mid-Atlantic Crop School, and so I am using many of her slides, and do want to acknowledge that. So, the first question we often have is why worry about soil fertility? Obviously, typically fertilizer is not free, but we all like to have our stack wagons overflowing, our hay wagons peak to the top, at least I do, and we all like to have our cows to have full bellies. And we know that soil fertility certainly is a big component of yield. It can significantly impact things like yield. Amanda did a nice job of talking about stand persistence, the percent of weeds and our forage species, what type of forage species are present, particularly when we're talking about nitrogen and potassium. That mix there can be affected. Our forage nutrient content and digestibility is going to be greatly affected by our soil fertility, particularly if we have some nutrients that are low. Drought and or disease resistance are all affected by that. Root growth, stand vigor, and finally economic viability. And of course, another reason we're blessed in this area to live in the Chesapeake Bay Basin, and a lot of recreational and other great opportunities that come about because of that. But it also comes with kind of a responsibility in this area because nutrients that leave the farm can negatively impact the bay, to take special care to make sure that we're not allowing that to happen and using nutrients responsibly. Forage systems actually are some of the best perennial systems, in particular for maintaining soil quality and building healthy soils, and actually can be have a very positive environmental impact. But we need to make sure that we manage that correctly. And it also gave me an excuse to put a picture up of my finally got a boat last summer. My little girl was just loving the water there. So just to recap, a couple years ago, we heard from Dr. Dennis Hancock, who was then at the University of Georgia, and he said this. He said the most common cause of poor establishment is soil pH and/or fertility that's too low. He said the most common cause of poor persistence is also low pH or low soil fertility. And finally, the most common cause of poor drought tolerance is also soil pH and/or low fertility. So fertility really is that thing that one thing that can affect all the different variables of forages. So it is really important. We want to make sure that we have balanced soil fertility to optimize establishment, production, and persistence. And just a quick example of this. This is some data from North Carolina, or pictures from North Carolina. On the left is an example of a field that was recently cleared. It was previously woodland, had a very low pH and low fertility level. It was not amended. The picture on the right-hand side was amended in terms of establishment. You can see the grasses there are well established on the right and very poorly established on the left. So, taking care of fertility up front can have a big impact on not only establishment, but the persistence of that stand. So when we talk about soil fertility, we're often talking about a balance. All our nutrients go through nutrient cycles and involve both from the input side and then the output side. And we're trying to keep that in balance. So inputs come from mineralization. So when we have organic material that's naturally in the soil that mineralizes and is converted into components that the plants can actually use. That's a major component for an input. fertilizers that we put on, manure, feed and minerals that we're feeding to our livestock. And a big one for forages, of course, is going to be nitrogen fixation by lagoons. And for outputs, we are taking, and this is with forages is particularly important, we remove a tremendous amount of nutrients when we take off biomass from forages. So we'll talk a little bit about that. So harvested forages into livestock or livestock products like milk that we're taking away from that field, and other loss pathways. So things like runoff, leaching, evaporation through gas. So, the idea here is that we want to make sure that we keep those in balance. We're not taking more off than what we're putting in. Otherwise, we end up mining that soil for nutrients, and the soil fertility levels are gonna decrease over time. And realize that out of almost any of our crop systems, so you think about something like corn or small grains, the only portion of that crop that we're actually removing is the actual grain. All the vegetative part we're putting back to the soil. But with forages, and in particular with hay systems, most of that biomass is actually coming off and being removed from that field. Now with livestock, pasture type systems, a lot of that gets recycled, but with hay we can actually remove quite a bit of those nutrients out quite quickly. And we look at what some of those numbers look like. I think Amanda shared this chart earlier. But it's somewhere around, depending upon the species that we're growing, somewhere between 40 to 50 pounds per ton of dry matter that we're taking off in nitrogen. A lot less in phosphorus, somewhere around 15 to 20 pounds of phosphorus, and then a tremendous amount of potash. So anywhere from 50 to 60 to even 70 pounds of potash per ton. So you start multiplying that up. Obviously, the more yield we get, the more nutrients we're actually removing per year. Another nice example that Amanda put together here that I think really needs to be considered is the amount of money you're actually taking off. So if you assume 1 ton of hay has about 45 pounds of nitrogen, 15 pounds of phosphate, and 55 pounds of potash per ton. An average cost right now for those nutrients, we figure about 40 cents a pound for actual nitrogen, 30 cents for phosphate, and 30 cents for potash. So you multiply that out, 1 ton of hay will remove 35 to 40 tons in actual nutrient value from that field. So that's pretty significant. And so we talked about distribution with pasture systems, with livestock. We know that livestock, hay, obviously we're removing probably 80 to 90% of those nutrients off the field. But with livestock, we're actually able to recycle and redistribute those nutrients back onto the field. So that's going forward there on me. So you can see this is just an example. This is from some information that Matt Poore shared a couple years ago at our Forage conference where we see this farm. And you can see the areas. In this area, this is where pigs were ran 50 years ago, and those areas are still much elevated with phosphorus levels. And you can see each of the concentrated, the feeding sites there around that farm. The watering sites and feeding areas are going to be very high. And then the areas away from that, where the cows don't concentrate, are much lower. And this is just another example of this in North Carolina, where they actually did some grid sampling across the one of the research farms, and you can see the feeding areas here and in this area and down in this area here. And if we look at that, you can see where the concentration of those nutrients are. So while a pasture or livestock-based system can recycle those nutrients, often the distribution is not equal across that pasture. That's something we need to recognize. And also, when we are doing soil testing, be cognizant that if you take a soil test in this corner and mix it with a soil test that you take from this end, a low area versus a high area, the result is going to be a value somewhere in the middle, and you're not going to be meeting either the needs of this end of the field or the other end of the field. So, grid sampling is a good way to try to get a more accurate account of actually what is going out in that field. And of course, our grazing management style is going to alter the distribution of those nutrients. As Amanda shared earlier, I think she said it was 27 years if you're doing continuous grazing, 27 years to get even distribution over that field. And you know, the way you feed your forages, your hay, so rolling that hay out can have the very good impact on trying to get that manure out to other parts of the field versus the cows all standing around the hay ring eating in one place. So simply moving those hay rings around can help a lot. Rolling the hay out, particularly on the poor parts of the field, is the best opportunity. And another example, again, from Matt Poor down at North Carolina, looking at very even manure distribution over the field. That's what we'd like to see instead of it being concentrated around a feeding ring. You know, simple things like dragging can also help a lot with trying to distribute those manure piles evenly across the field. You know, hay feeding management does matter. Think about how those nutrients are redistributed across the field. Again, the stationary ring is going to result in accumulation of those nutrients in one spot. Moving the ring around can help quite a bit. Unrolling the hay is probably the best method there. And you know, one of the things that we do like to do is if we can feed that hay and get those nutrients to the poor areas of the field. When I say poor, I mean those areas of the field that have lower soil fertility, not necessarily poor soils. And moving those feeding spots around as much as possible can really help. So we can't do a nutrient management or soil fertility talk without talking about soil testing. You know, soil testing really is the basis for all of our nutrient management recommendations, other than nitrogen. It's what we use to identify, you know, the amount of the particular nutrients that are out there at the pH level of the soil. And so for most nutrients, except for nitrogen, it's what we're going to base our fertilizer rates on. A common saying, without a test, it's just a guess. So really taking the time to get accurate soil samples is really the first step in developing good recommendations. So, and just as a reminder, nitrogen recommendations are going to be based upon the crop, so what species you're growing out there and what your actual yield goal is. And this is mainly for our grass type crops. Most of our legumes are going to produce their own nitrogen, but for our grass forages, we're going to base that upon what species we're growing and what the yield goal of that actual crop is. But all the other nutrients, so phosphorus, potassium, calcium, magnesium, and our micronutrients are all going to be based upon that soil test. So the lower the soil test value, the higher the nutrient recommendation we're actually going to get. So Amanda talked a lot about soil pH, so I'm not going to spend that much time on it. Just a reminder, again, you can see that the area that we want to be in here is between the 6 and 7 range, where most of those nutrients are most widely available. Just a couple of points that I think it's important to emphasize, particularly for pasture systems. We have a lot of unimproved pastures or hay fields that are grown on ground that has, you know, pH of 4.5 or 5 or 5.5. And what we start to see when we get down to that area is this aluminum, you know, once we drop below about 5.3, aluminum becomes much more widely available in the soil. And aluminum is toxic to plant roots. It really limits the amount of root growth you're going to get. And so that limits the amount of soil that those roots can explore and the amount of nutrients that those plants can take up. It also does a couple other things, particularly for legumes in a lower pH soil. You see molybdenum here is not available once we get down below 5.5 or so, and much less available at even a pH of 6 or 6.5. And molybdenum is really important for nodulation. So for our legumes, you know, we think about a crop like alfalfa. We know it likes a pH of 6.5 to 7. And one of those reasons is because of the molybdenum availability. So it's very difficult, it'd be almost impossible to raise an alfalfa crop down at a pH of 5.5. So just keep that in mind as well. Some other things we see, manganese on the other hand becomes much more available, so does iron at lower pHs. And so you can actually have some toxicity issues out at lower pHs, but more often what we see, particularly in my area in the coastal plain, on small grains, things like barley and wheat, is when we start growing those up on a pH of 7.1, 7.2, 7.3, we actually see manganese deficiency on those plants. So if you're growing small grain, that's one that's often seen. So just realize, you know, we often say lime is the cheapest fertilizer you can buy because pH affects the availability of all the other nutrients. And it's also, you know, lime is going to be the main source of magnesium and calcium for that soil. I also, Amanda put this chart together that I think really emphasizes the point behind using lime to get that pH up. When we compare the economic difference between a pH of 5.6 and that is 6.2. So you can see the amount used annually of nitrogen, phosphorus, and potash. Let's say we're using about 200 pounds of nitrogen, 50 pounds of phosphate, and 150 pounds of potash, and we multiply that out, comes up to about $140 an acre that you're spending to fertilize that crop annually. But let's say we try to grow that at a pH of 5.6, where we have much less use of those nutrients. In other words, our efficiency is nearly not as good. 35% reduction in nitrogen, 50% in phosphate, and 10% reduction in availability of potash. And you can see we actually have a value of decrease of $41 an acre. So it's actually costing us, by not liming, about 40 bucks an acre. And by the way, that's about what it would cost in lime to bring that pH up for the next several years. So consider that. Consider the, you know, if you're growing at low pH because you don't want to put the money in lime, really in the long run, it actually pays for itself fairly quickly. And again, just remember what I showed about aluminum toxicity. It's not just what is available, what's not available, but what becomes available, and that's aluminum at lower pHs. And here you can see on the left is a plant that was grown in soil that was not amended with lime, and on the right that was amended. You can see the amount of root mass there, and you can imagine with all those finer root hairs in there, the ability of that plant to take up nutrients is going to be much greater on the right than it is on the left. And the only difference there is soil pH. In my area, this is particularly true. In the coastal plain area here in southern Maryland, also on the eastern shore, I would think as well. Our subsoil, once we get down about 8 inches or so, our pHs drop down to about 4.8. So we've spent a lot of time trying to get those subsoil pHs up to get further root exploration down through that soil horizon. So we think about, you know, what are some of the optimal soil pHs, and you know, alfalfa is the one we often think about the most, 6.5 to 7 or so. Don't grow peanuts in this area, but we look at some of these others like Sericea lespedeza. It can grow at a much lower pH and also can actually grow quite well on lower fertility soils as well. And some of our clovers, they have a, you know, we can grow them really well at around 6.5 to 7, but they can tolerate a little lower pH in there. And then some of our other legumes down here on the bottom can tolerate even a lower pH and can still nodulate and produce their own nitrogen down there, which is really what it comes down to, is how much nitrogen can they produce and how can they nodulate at that lower pH. So again, just ensure that your pH is up where it needs to be. Typically that's going to be done with lime. You know, realize what the calcium equivalency of that lime is and what you're actually putting out there. We you know, the standard ag lime is 100% CCE. If you go below or above that, you need to adjust that liming rate accordingly. And it, just as an example, we know that pH of the soil is going to affect the composition of species that are going to be in that stand. Those species that can tolerate lower pHs are going to proliferate in lower pH soil, and this is the classic example of broom sedge that can tolerate both low pH and also low phosphorus. But also you think of something like tall fescue. If you have a grass legume mix and you're growing at a much lower pH, tall fescue is going to be able to tolerate that much better than the clover, and it's going to proliferate. Within 1 or 2 years, you're not going to have much clover left. So broom sedge is actually one that's affected by both pH and by phosphorus level. Low pH can do it, but phosphorus is typically oftentimes the culprit. This is some work done at the University of Missouri. where it just shows the field to the right there had lime applied. The portion of the field to the left did not, and you can see the proliferation of the broom sedge. And we look at that same thing, over time, looking at both liming and phosphorus addition. So over a 3-year period, it started out in 2005 here with about 20% broom sedge, and over 3 years, that stand had up to 60% broom sedge in it if you didn't put any lime or phosphorus on it. But if you added a standard rate of lime and up to 50 pounds of phosphorus, you can see that's the lowest amount of broom sedge. And same thing if we look at the amount of tall fescue. Obviously, the more lime or more phosphorus that you add, you get an increase in the amount of actual tall fescue in that pasture. So pH is kind of where we start when we talk about fertility with either hay or pasture fields, making sure that we get that fertility where we want it for the species that we're actually growing. All right, so moving on, talking about what those essential nutrients are for plant growth. We start with our macros, so nitrogen, phosphorus, and potassium, then our secondary nutrients, sulfur, calcium, and magnesium, and then we move over to our micronutrients, which boron, particularly with alfalfa and other legumes, is really important. Molybdenum, also another important one. Zinc can also be sometimes deficient. And we always like to stress that any one of those nutrients that is limited is going to limit the entire production of the system. So this is what's referred to as Liebig's law of the minimum. You look at a barrel, and whatever stave is the lowest there is going to really limit the production of that entire field. So we need to make sure that all 16 of those nutrients are adequate. So when we actually talk about how much is the right amount of nutrients to apply, we look at the yield response curve. And so particularly for things like phosphorus and potash, where we can rely on soil test data to inform our decisions on how much material to apply. If we start down here in the very low category, so very low phosphorus or potash, we're going to get a very high recommendation for nutrients, because we need to apply enough material, enough nutrients to supply what the plant actually needs, but we also want to try to build up this level over time to get into this, what we call the optimal range, where we're only applying maintenance fertilizer. So you're going to see that yield, you're going to get a great yield response when we apply fertilizer, and then that response is going to kind of leveling off. And finally here, when we get into the very high and excessive range, you don't get much yield response at all to fertilizer. So we'd only be applying maintenance fertilizer here, what fertilizer we're actually removing to try to maintain that soil test level. Now, when we get over here into the excessive range, we actually can kind of bank or use that amount of nutrients that are stored in the soil and try to get this line, get the soil level to come back in here into the optimal range. So we'll start here with nitrogen. So we know that nitrogen, out of any of the elements, is going to affect plant growth the most. It's very quickly apparent when you put down nitrogen, you get a very quick growth response, and it also affects yield greatly. It is a major component of amino acids of plant proteins, and so it is critical for plant growth. And nitrogen is also very dynamic in the soil. It changes all the time. The form that it's in, nitrogen cycles is pretty complex. So we can't reliably test for nitrogen levels, because the test that we take now, 2 weeks from now, might be completely different. It also is very mobile in the soil, which means that it's prone to leaching, and that's particularly true on sandier soils. The more sandy the soil, the more that nitrogen will leach through that soil profile. So that's where timing is really critical with nitrogen. Generally, plants take off about 40 to 50 pounds of nitrogen for every ton of forage that you remove. Most forages, particularly grass forages, you're going to get a recommendation between 100 to 200 pounds of nitrogen per acre per year. That's going to vary based upon your plant yield. and it can vary pretty considerably. So this is one where, you know, if you go from 2 tons per acre of a cool season grass up to 4 to 5 tons per acre, you know, you're going to be doubling the amount of nitrogen that's actually required. So it's directly correlated to expected plant yield. So some common nitrogen sources in this area, urea, UAN solution or liquid nitrogen is often used. Urea ammonium nitrate is another one, or calcium ammonium nitrate in our area is now beginning to be used. Ammonium sulfate is also, particularly for forages, for a spring application, a lot of folks now are using ammonium sulfate mixed, half ammonium sulfate, half urea, and that gives you about 20 to 30 pounds of sulfur in most cases. We'll talk about sulfur here in a little bit, but sulfur is one of those nutrients now that we're seeing become limited as depositions from air pollution are going down. We're just not getting that amount of sulfur that we did, you know, 30 or 40 years ago. And of course, in our area, another good source is going to be poultry litter or manure. Both are good components of good carriers of nitrogen. We'll talk about that in a little bit. The other thing to remember with nitrogen is you want to consider subsurface placement or incorporation of nitrogen fertilizer if you can. Obviously on hay or pasture systems that's difficult to do, but if you can put it on just before rain, a light rain to get that incorporated, or if you're using something like urea or UAN solution, you might want to consider the use of a urease inhibitor to try to decrease those volatilization losses, those surface losses that you get from using those products. So when we look at nitrogen timing, and this is one that's changed over the last 5 years quite considerably. I'm still trying to get used to that change. We'll talk about the late application here in a minute, but it's really important. You know, the thing that we've always stressed as an extension agent, you know, one thing that's drilled into our heads over and over again is that you want to put the nitrogen on when the plant's going to be utilizing that nitrogen, so just prior to vegetative growth in most cases. And typically that means you're going to be doing some split applications. So we'll put that on in the spring, and then following the first cutting, and a late summer application, and now we're doing a late fall application as well. But that can vary somewhat between hay and pasture. So for hay production, typically we'll come in with an application right at green up here. So it's going to depend on what area you're in. In my area, that would be around March 10th or so, we see green up. We want to get a little bit of nitrogen on so we get some good growth and we get a nice good first cutting with hay. And then we're going to put on that late summer application again to try to get that nice growth during that second growth period into the fall. With pasture production, that can change a little bit, and that we might delay that first nitrogen application a little bit further into the spring, so that we kind of push that production a little further into the summer, so that you get that forage that will respond. Instead of getting that hump of growth here, we're going to get that hump of growth a little further into the summer. Also, some other things to consider with nitrogen timing. Typically, again, at green up after our first harvest, late summer, and then we're going to be doing a late fall application, which is a little bit of a change. For warm season perennials, so in my area, that would be things like Bermuda grass, which is becoming more and more popular. We're going to wait to put that nitrogen on at green up, because the longer it stays in the environment, the more prone it is to leaching. So if I put that on in March, by the time May comes for Bermuda grass for green up, I've lost a considerable amount of that. So I'm going to put that on at green up for Bermuda grass in this area. It's going to be about the first week of May. And then after each harvest, I'm going to split that throughout the season to make sure that we have available nitrogen there for when that plant is actually growing. Same thing for our annual forages. We want to do it at establishment and then after each harvest. So our late season nitrogen application, again, this is a little bit of a change. This is something that Dr. Vo worked on when he was our forage specialist. And about 4 years ago, I think we made the change in our nutrient management recommendations. So this one's been a little bit difficult for me to kind of adapt, because, you know, we've always been of the mindset you're going to put your nitrogen on when that plant is growing. But when we're talking about a perennial crop, that's typically true for an annual crop, but most of our forage crop for our cool season grasses are a perennial crop, and while they might not have a lot of vegetative top growth during the winter, those root systems are still active and are still taking up nutrients. And so in the turf industry, they've been doing this for a long time, and now we're starting to actually adopt it in the forage industry. So it can aid in the uptake of water and actually other nutrients, and also can help with carbohydrate buildup in stem bases. The other big thing it does, and we know this with small grains, when we plant wheat or barley, we know how important the tiller count is going to be to yield, and tiller count is primarily a function of nitrogen availability in the soil. And the same thing is true for a perennial crop, that late season in application can actually increase formation of new crown buds, so new tillers that are then going to be productive the next season. The other thing that a late season nitrogen application can do is permit early initiation of spring growth. So you have those that energy build up in the stem, and as soon as that weather cooperates in the spring and we green up, that plant is off and growing. It is important though that we do use highly soluble nitrogen sources. If we're going to do that late season application, we don't want to have a product that's going to release in January or this time of the year, because a lot of that material is going to be lost. We want a material that's readily available to that plant. Highly soluble nitrogen source. And this is actually Dr. Vo's yard, his previous yard, where he did on the right-hand side, did an application in the fall, and on the left-hand side did not. And you can see the difference in the green up in the spring. You can see how much greener it is on the right. Same thing in this picture. On the left got the fall application, the right did not. If we look at those nitrogen recommendations, again, this is concentrating on cool season perennials. If we get the green up application is actually removed for lower yielding fields. So up to 3 tons, you're not putting on that application of green up, but you are putting on an application down here in late fall. So we're going to do a late fall application in late October, early November. We're going to come in after our first harvest in May with a second application, and then a top dress in late summer for our third application. Then when we move to productive fields, so when we're talking about 4, 5, 6 tons and up, then we're going to go back to that spring application. So 35 to 50 pounds at green up, 40 to 50 after our first harvest, top dress in late summer towards the end of August, and then again in late fall. So late application, that kind of depends on where you're at. We have a lot of diversity in our climate here in Maryland. So if you're out in Western Maryland, that might be mid-October. If we're in the coastal plain in Southern Maryland, that might be mid-November. So those are the new recommendations for cool season perennials here in Maryland. I did want to touch base on nitrogen from legumes, particularly in forage systems. This one is really important. It's quite an amazing relationship between the rhizobium bacteria and the legume plant, which that symbiotic relationship allows the plant to fix anywhere from 50 to 250 pounds of nitrogen per acre per year. And with alfalfa, it actually can be even a little bit more than that. And we look at the amount of nitrogen that can be available for alfalfa: 150 to 250, red clover 75 to 200, white clover 75 to 150, and some of our annual clovers or luscidies, it's a little bit less, from 50 to 150 pounds of actual nitrogen that's fixed. And that has a real value to us. At 40 cents a pound of nitrogen, you can see anywhere from $60 to $100 for alfalfa. If it's 80 cents a pound for that pound of nitrogen, obviously it's double, $120 to $200 an acre value. So it's really is an amazing relationship that allows that plant to produce its own nitrogen, to fix nitrogen, atmospheric nitrogen, into a form that the plant can use. And it's one thing to remember, that it is a function of yield. So the higher the yield of the legume, the more nitrogen that's going to produce. So the more growth you get out, and this is true with cover crops as well, the more biomass, the more growth you get out of your clover, out of your alfalfa, or out of your vetch, the more nitrogen that's being fixed as well. But we do need to remember, it's not just because you have a mixed stand of legume and grass, it's not like all the nitrogen that the legume fixes is automatically available to the grass crop. It's shared indirectly. On pasture systems, the main way that it's shared is being recycled through the actual animals. So ingestion and deposition of that feces and urine back onto the pasture. And of course, this is where we talk about distribution. If they're ingesting, in one part of the pasture, and then they're coming back under the shade tree or wherever they're congregating, where they're peeing and pooping, then most of that material is going to be in one spot. So again, that's where even distribution really matters. There's also some other ways that it's shared through death and decomposition of plant parts, particularly when there's roots and root parts begin to slough off, that material becomes available. But good soil biology and soil quality here really helps with that nutrient cycling. This is a chart that was shared with us a few years ago, which looks at that sharing of nitrogen between a clover and grass species. And we see that there is a little bit of direct transfer through mycorrhizal hyphae from one plant to the next, but it's very minor. Then we have a decay of some plant tissues, and as those nodules or root parts kind of slough off and decay, you'll get a little bit of a breakdown and availability there. But a lot of it is by exudation, by living cells of that material that's then converted into ammonium and amino acids, broken down by microorganisms, and then that material is actually available to the grass plant. So it is kind of a complex cycle there that depends upon good soil quality. So the better soil quality you have, in other words, good friable soil with lots of biological activity, is going to increase the amount of that material that's available to the grass plant. Also, another point that I'd like to make here is that legumes need to make up at least 25% of that sward to really have an impact on the amount of nitrogen that's going to be available for those grasses. So, and this is something with our recommendations that we produce at University of Maryland. It's kind of black and white line. It's either under 25 or over 25, but really that is a continuum. So you kind of need to consider that. Just because you have 25% legumes doesn't mean that 100% of your nitrogen is going to be available. It's not. Also realize that fertilization with nitrogen is going to favor the grass. So you're going to end up with predominantly more grasses if you fertilize with nitrogen, versus fertilizing with phosphorus and potash is going to result in more legumes. All right, so we're going to move on here to phosphorus. Phosphorus is a little bit different in nitrogen. That phosphorus is absorbed to soil particles and to organic matter, and so it's not easily leached. It basically stays where you put it unless you get really high levels or the actual soil particle washes off. It's very important for plant reproduction. It's also very important for root growth and seedling development. That's why oftentimes our starter fertilizers are going to have quite a bit of phosphorus or high phosphorus levels in them. Plants use phosphorus as phosphate, P2O5, and typically it's around 10 to 20, around 15 pounds of phosphate that are going to be removed per ton of actual forage. And again, we're going to apply this based on soil test results. I'll show you an example here in a minute. Typically for phosphorus, we're going to use triple superphosphate, or we're going to use a MAP or DAP compound where we're getting some nitrogen out of that as well. Another excellent source of phosphorus is manure or chicken litter or biosolids. So this is an actual recommendation that I pulled for Newman, our nutrient recommendation software. And you can see the, we look across here on the x-axis is the soil test value. So we have a very low value, and you're going to get a much higher recommendation, 150 pounds of phosphorus. And that recommendation gradually decreases as we get into the optimal level. And basically, the optimal level here, we're just putting on around 20 pounds of actual phosphorus. And when we get down to, above 100 into the excessive level, that's going to drop off to 0. But one thing to note is that depending upon the productivity of your hay or pasture fields, this is crop removal or crop uptake rates for nitrogen, phosphorus, and potash. So we're using about 19 pounds of phosphorus. So if we look at this 4 tons per acre, we're actually taking off around 80 pounds of phosphorus. So even in this area here, we're putting on 20 and we're taking off 80. So you're actually really mining the soil. We're only building up the soil when we're putting on over 80 pounds. So just be cognizant of that. On high productivity fields, you can actually take off more phosphorus than what we're recommending you put on. Now, lower phosphorus fields, 2 tons to the acre, this recommendations are going to be a little bit more suitable. And the same thing is true for alfalfa. Again, we're taking off about 15 pounds per ton, but if you're taking off 6 tons, you're up at 85, 90 pounds that you're actually taking off. And you can see here, we're not putting that much quite back on. So we need to really watch it on our highly productive fields, how much phosphorus we're taking off versus putting on. In terms of phosphorus timing, this is one where we're really not as concerned. Typically with hay systems, we can kind of put this on in the fall when phosphorus demand is not quite as high at the dealers, distributors. You get a little bit better prices. So phosphorus is going to stay where you put it. We don't have to be so worried about that. If we're going to be really using high rates, if you have some really low soil phosphorus levels, we might think about split applying. The other thing with hay systems, we're only applying on the surface. Typically, we can build up some higher phosphorus levels on the surface of that soil. So anytime we're doing tillage, if you are renovating or are going to be doing some tillage, you might consider how you can get that phosphorus a little bit deeper into that soil profile. I want to talk a little bit about potassium. Not going to spend too much time on this because Amanda covered it fairly well. Just realize that it is really important for disease resistance, persistence, winter hardiness, tolerance. And as Amanda showed this picture a little earlier, you can see the field there on the left had potassium, the field on the right did not. Much better persistence with potassium. It doesn't move nearly as much as nitrogen does, but on sandier soils it can move some, especially the plant available form. So we do need to watch that some, but it's not nearly as mobile as something like nitrogen. And we do need quite a bit of it, normally around 50 pounds per ton of forage, which can be significant. So for a crop like alfalfa, we can look at recommendations all the way up to 550 pounds an acre annually for lower potash. If we start with a lower level in the soil, we have a high yielding alfalfa field, we can use significant amounts of potash. For grasses, typically it's going to be between 100 and 200 pounds annually if your soil test is low. And this is just an example of our actual potassium recommendations for tall fescue at 4 tons per acre. And again, starting up there at 200 pounds if your soil test level is really low, and then gradually coming down to 0 once you get into that excessive range. But again, you need to really watch what you're taking off. So 53 pounds per ton. So you're taking off nearly 200 pounds of potash if you remove all of that tall fescue in a hay system. Now in a pasture system, obviously you're recycling most of that back onto that field, and so that's not an issue. But with hay systems, this is where we tend to get into trouble, not putting on enough potash for what we're taking back off. And same thing with alfalfa. This is recommendations for 6 tons per acre, and you can see here if we start out with 0, so no potash in the soil bank, and we're getting recommendations all the way up at 400 pounds, and it only goes down to about 230 pounds even when we get into that very high range, because we're taking so much off, about 60 pounds per ton. So again, you know, I'm a big fan of split applying potassium, half in the spring, half in late summer or fall. If you already have really good levels in the soil, it's not nearly as critical. But if you have lower levels, I do like to split apply that. And again, potassium. This is some information that Dr. Hancock shared a few years ago with us. Really important for yield and also for persistence. So it really affects the shoots per area, the leaf mass per shoot, and the stem mass per shoot as well. Phosphorus is also important with potassium, so they kind of work together. Phosphorus tends to have a little bit more impact on shoots per area than potassium does. And you saw the earlier picture of root growth where you had adequate phosphorus and potassium available to that plant that Amanda showed. So all the information that I am sharing with you today comes from our plant nutrient recommendations, our agronomy recommendations that are available. We use a software program called Newman to formulate recommendations, but you can also do it by hand by following the recommendations that are available here. There is the link where you can download this file. But it basically has, you know, for each species what the recommended rates are. Talk a little bit about, we're running out of time here, but we'll quickly talk about some of our secondary micronutrients. And the one I want to focus on is sulfur. So calcium, magnesium, and sulfur. Sulfur in particular here lately is we're seeing more and more issues with deficiency both in grain crops and in forage crops. So sulfur is key component for protein formation and for nitrogen fixation and root growth. In the past, we often got a lot of sulfur kind of for free through deposition from the atmosphere, from power plants that were burning fossil fuels, but those plants are not nearly as many of them, and they're burned much cleaner now. So poultry litter, animal manure is a good source, but also looking at things like ammonium sulfate is another good source for sulfur. And then for calcium, magnesium, typically this goes along with liming. If we do a good job of liming and adjust what type of lime we're using, whether it be the calcitic or the dolomitic lime, depending on whether we need the calcium or magnesium, we can keep those levels up. For micronutrients, boron and molybdenum, particularly for legume crops, are really important. And so we want to watch those carefully. For alfalfa and other legumes, we're typically putting on an annual application, you know, 3 to 4 pounds per acre per year. Molybdenum, again, really important for nodule formulation. This is where if you have lower pH soils, that's going to be a problem for you. A small amount of molybdenum every year can help with that nodulation. So some other options, you know, we talk about manure, commercial fertilizer, legumes, biosolids are all sources for fertility. Just realize that not all of the nutrients that are in a particular manure are going to be available that first year. So this is for dairy manure. Only about 3 pounds of that organic material is going to mineralize and be available to the plant in that first year. This other 6 pounds is not going to be available until future years. And also realize that the ammonium component of that is going to depend upon when you incorporate it. So if you don't incorporate it, you're going to lose the majority of the ammonium component. If you do incorporate it fairly readily, you're going to be able to keep most of that ammonium component. Same thing is true with poultry litter. So poultry litter is going to vary in composition of nitrogen, phosphorus, and potash, but typically most poultry litters are going to have around 35 to 50 pounds of actual nitrogen available that first year. The mineralization rate for poultry litter is about 50%. So if you have a total of 40 pounds of organic nitrogen, 20 pounds of that will be available the first year, and then about 16 pounds of the ammonium nitrogen will be available if you can get that incorporated or you get a light rain after you put it on. So in this case, that would be 36 pounds of actual plant available nitrogen. In our area, we do use some biosolids. Just realize with biosolids, a good source of nitrogen, good source of phosphorus if you need it, but very little potash. So this is when, if you're going to use biosolids, make sure you you're supplementing that with some potash, and also really watch your pH. I'm gonna stop here. I'm gonna go through a couple of these here. I think Amanda talked about persistence. I'll just close with some quick conclusions. So good forage production is going to depend on optimal pH. You have to replace those nutrients that you are removing. And remember, with hay systems in particular, we are removing a lot of biomass, so you are removing a lot of nutrients with that. And soil testing is the foundation for good, sound decisions on what nutrients you need. Nitrogen is going to be based upon what actual yield you want. It is mobile and should be split applied. Legumes are a great source of nitrogen and something you should consider to save on nitrogen fertilizer costs. And phosphorus and potash levels need to be managed in the soil to keep those levels at an optimal range. So with that, I'll finish. I know we're running a little bit behind schedule here. If you have any questions, there's my email, and I'll turn it back over to you, Amanda.
Great. Thanks, Ben. We do have a couple of quick questions. The first person said that they used to have a lot of broom sedge when the nutrients in the hayfield weren't managed. Since fertilizing and liming, over the last 4 years, the broom sedge disappeared up until late last summer. And he's wondering if there was a broom sedge flush, maybe due to drought or something. They're all still in the range. Do you have any thoughts on that?
Yeah, so we can see broom sedge in pastures that have adequate pH and adequate fertility, but typically it's some other environmental condition that promoted the broom sedge growth and not the desired forage growth. So drought is the most common one. Overgrazing or cutting those pastures or hayfields too short is another big one that we commonly see. And so what you see there is you see the tall fescue orchard grass really struggle to come back, but the broom sedge, if there's still some remaining in there, is a little bit better adapted and can manage to come back a little stronger. But over time, normally if you get the fertility up, the broom sedge will disappear.
Okay. Someone asked if you could talk about how to raise soil pH in that lower 6 to 12 inches if soils are more on the sandy side.
Yeah, so that's a good question. I don't have a great answer. Some of the things that we've looked at is actually use of gypsum. Gypsum is a much cheaper product for us to use. It doesn't have a big impact on soil pH, but it can really increase the amount of calcium that we get down on the lower soil horizon, and that can kind of make up for some of that aluminum toxicity that we see. So we've done some work with gypsum. The other thing is, if you have the opportunity, if you are going to be doing any type of tillage, is to try to get that lime incorporated down as far as you can.
Okay, the next question is, if we are utilizing rotational grazing, how long should goats stay off of the pasture after applying the NPK and lime?
Yeah, so it kind of depends on how it was applied. These typically are going to be salts, particularly nitrogen and potash, and so sometimes animals are attracted to that. Normally it's not a problem at all. You don't have to worry about keeping them off at all, but if you do have animals that tend to be attracted to the salts, you might want to wait until you get a light rain. Normally we don't have to keep them off at all from this evening. So.
Okay, there was a request for you to show your slide on bloom, and they asked if you have any opinions on bloom usage.
Sure, let me see if I can get this. So we've done some work with bloom in my area. Yeah, so bloom is from the Blue Plains treatment facility. They put in a new treatment process where they're using, it's a fairly complicated thermal hydrolysis process. the end product is this product called Bloom, which is an exceptional quality biosolid, which means you can use it on things like vegetable crops and places where you wouldn't be able to use other biosolids. So the take-home message, it has about 10 pounds of nitrogen available, plant available nitrogen that first year, and has a really large dose of phosphorus, so about 40 pounds of phosphorus, and very little potash. So if you're in an area where you need lots of phosphorus, it's an awesome product. It's very cheap. In our area, it only costs $4 to $5 per ton delivered to the farm. It's an excellent product for getting your phosphorus levels up. And I'll show you some trials that we did with corn, just so you can see what it actually looks like in the field. This was on a sandy soil in Charles County. My recommendation typically for forage system would be to use, somewhere between 3 to 5 tons. You get much more than that, you're going to end up with some issues with particularly for hay systems, with getting that hay cut just because of the bulk of the material. But that'll give you anywhere from 30, 50, 60 pounds of nitrogen, and then supplement the rest with synthetic nitrogen, and you'll get a good dose of phosphorus for that year. You can see in the trial that we did, we got very good response. This is on corn, but you can see 3 tons versus 10 tons versus 17 tons. Our best yields in this field where we used somewhere around 6 or 10 tons, and then we supplemented that with a synthetic nitrogen, and we got very good yields. So that would be my recommendation, but it's best suited where you actually need the phosphorus.
On that same note, someone asked where they could get Bloom from.
So Bloom is produced at the Blue Plains, so it's the Washington WSSA Blue Plains plant. They, if you look up Blue Drop or just look up Bloom, they have a procurement office there, and they will deliver it most places in the state. So the nice thing is they cover most of the cost of transportation. You just have to pay, again, it's like $4 to $5 a ton for the product delivered to the farm. So it's Blue Drop is the name of the company that actually distributes it, I believe.
Someone said, at what level of magnesium would it cause you to use dolomitic lime?
Yeah, so I'm not a big fan of trying to use ratios, having an exact ratio, but the main thing, the bottom line is that we need to have adequate levels of both calcium and magnesium in the soil. And so when you look at your FIV value, if you have your fertility index value, so if you have a very high level of calcium, let's say it's 120, and your magnesium level is down at 30 or 40, that would indicate that you have a much greater need for magnesium than you do for calcium. And so we would use dolomitic lime in that instance. If both levels are adequate, so if you have FIV value of 80 or 100 for both calcium and magnesium, you could really use either dolomitic or calcitic lime, either one, whichever one would be cheaper for the liming value that you're getting, if that makes sense.
Great, thank you. Someone said that they've seen ads for liquid calcium. Any advantages to using this?
Yeah, so personally, I'm not a big fan of liquid calcium. Your bottom line is you need to get the soil pH level up, and for the amount of actual neutralizing value you're getting for liquid calcium is not really going to do much in terms of raising the overall soil pH value. We really need to invest in actual liming material where you're going to get enough material on there to do a significant change in pH.
Oh, I missed, someone had asked if the Bloom is pelletized or what.
It is not. It is not pelletized. It is a bulk material. It is somewhere around 75 to 80% water. And so that's one of the biggest disadvantages. You know, typically we would use a manure spreader. A poultry litter spreader is the best thing to use, or you can use a small, smaller manure spreader, but it is a bulky product and you have to use a lot of it. You know, you're spreading a lot of it versus a product like granulite, which we get out of Baltimore, that is pelletized. You know, that's going to be a lot easier to spread. It's also a lot more expensive though.
One more question on the bloom topic. Are there any heavy metal concerns with bloom?
Right, so it is a biosolid. The process that they're using is a pretty advanced process. They do as required from MDE. You know, they do the analysis that looks at levels of heavy metals. I have not seen anything that I would be concerned with, but if that's an issue that you have, you want more information, you can ask them for the analysis that they send to MDE that has all of the heavy metal concentrations in it. I haven't seen it to be a big issue. Bloom does have a fairly high percentage of actual iron in it. Our soils have a lot of iron anyway. It's not something to worry about. So. Yeah, I guess the short answer is I haven't seen anything in the analysis that I would be concerned with.
Great, thank you. I believe that is everything. We just want to thank everybody for joining us today. Hope that you had a good experience. We wish we could have seen you in person, but hopefully next year.